So just in case, yeah. All right, welcome everybody to this week's edition of the Simulation-Based Science Colloquium. Before I introduce Paul, let me briefly introduce a website in case you weren't familiar with it yet. So this is the Simulation-Based Science Community website, community.nl, where you can sort of browse, the people that are part of that community, and you can, look at their academic field. Maybe you want to make some connections to people working in the life sciences, browse what they're interested in, what kind of methods they're using. And if you're not on that webpage, you can join it if you're affiliated with the University of Amsterdam. Just fill out a form. But what's maybe most interesting to you is that we started putting up the past events. So here's the abstract and the slides, and as soon as available, the recording of previous talks. If you want to, watch them again in case you missed them, maybe you just want to, watch them with your family. I think this is a classic. So yeah, check it out. But for today, I think we're very excited to welcome Paul Smaldino, who's an associate professor in cognitive information sciences at the University of California, Merced. He did undergraduate in physics and a PhD in psychology, and various postdocs in departments of medicine, political science, computer science, anthropology. So he's a very interdisciplinary guy. And he has published widely on signaling, cooperation, meta science, and the use of formal models in social and behavioral sciences with, real classics like, models are stupid and we need more of them, or the natural selection of bad science. And I think what we've noticed so far in this colloquium is also that simulation-based science methods lend themselves very naturally to interdisciplinary work, which is a topic Paul is going to talk about today. So yeah, I'm excited to hear more about it. Paul, take it away.
Thanks, Fabian. Thanks everyone for inviting me and for having me here. Let me just share the screen. So I'll say this is I'm going to be presenting pretty new work. This is actually the first time I'm presenting this particular study. So you're my guinea pigs and I'm sort of working through the kinks. So apologies for any roughness in the talk. I think the point that was just made, though, that doing sort of simulations and modeling lends itself very well to interdisciplinary work is relevant, because I think that just, it's always just been very natural to me that oh, look, there are models, I can do things with them and study things and draw from all different areas. And then the longer I was doing it, the more frustrated I sometimes got that other people weren't quite as willing to be interdisciplinary. So I'm going to talk sort of broadly about that, but I'll also be sort of focusing on this this project, which is a paper done with Kaylin O'Connor, whose work some of you may know. She's a philosopher and game theorist and modeler at UC Irvine. The paper is currently under review, but it's a preprint that's available on Meta Archive, so you guys can check it out. The question that we were using the model to structure a conversation around are sort of this, like why is it that bad methods persist in some academic disciplines, even when they've been rejected in others? And conversely, what factors allow good methodological advances to spread? So I'm going to now talk about a field that I never thought I would be engaging with, which is sports science. So here's an article that came out in 2014 called Foam Rolling as a Recovery Tool After an Intense Bout of Physical Activity. So foam rolling is just this, right? It's just getting one of these tubes and rolling around on it. And some of you may have done this, or you may have a foam roller at home. And there was this paper that came out talking about how great this was and what a good benefit it was for people's health. The paper was very influential. Like, the foam rolling industry is very, I guess, proactive, and people like these things. So since 2014, it's been cited over 300 times. So people are this matters. People are paying attention to it. What's notable about the article is that in their analysis of their data, which they did by getting people who had had sort of physical injuries and stuff and then foam rolled or not, they used a particularly unusual and novel statistical method, which is called magnitude-based inference, or MBI. I didn't know about this until very recently. It originally, it's with a series of papers by Hopkins and Batterham et al. And it was developed by sports scientists to analyze sports science data and is basically exclusively used by sports scientists. Now, this paper, in which they describe the method, came out in 2009. It has been cited over 5,000 times. So from 2009, it's pretty influential. Now, here's the thing, right? What this does, MBI, it sort of ostensibly compares the risk that an intervention causes harm with the chance that it benefits an athlete. So, and sort of does this cost benefit analysis, and then sort of if it's likely enough that there's actually a benefit and not harm, then it says there is a significant or a substantial effect. The thing in this paper, which is the main paper that describes the effect, there are no equations, there are no algorithms. There's a verbal description of the method and a link to an Excel spreadsheet. Right? And they say, you can use this spreadsheet to calculate your own significance with your data. This struck me as unusual, but I'm not a sports scientist, so maybe that's just how they roll. However, it did attract the attention of a number of statisticians who were like, what is this method that we haven't heard of that these sports scientists are using? And here's a paper in which they systematically reviewed a bunch of papers that used this inference tool in sports science and found that in many, many, many cases, if you reanalyze the data using more traditional statistics, all the effects go away. So this is a table analyzing that McDonald et al. Foam rolling study and finding that all the effects that were reported in that paper are non-significant if you analyze them with more traditional frequentist statistics, which seems like a problem. So the statistician and epidemiologist Kristen Sinani wrote this really nice review of exactly what is happening with magnitude-based inference. And she found out that, because it sort of weighs the costs and benefits, it's heavily weighted toward false positives. So this is a figure looking at false positive rates, the rate of type 1 errors, under an assumption of no effect. So a traditional frequentist statistics with a p-value of 0.05, if you give it a false, a no effect study, occasionally you're going to have 5% chance of getting a false positive. At around a sample size of 50, there's almost a 15% chance of a false positive with magnitude-based inference, which is basically exactly the main sort of range of sample sizes used in sports science. And it seems like a problem. There was this, we found out about it through this work by Christy Ashwandon and others at 538, who's a sports science journalist. And I really like this quote. This is by Andrew Vickers, who's a statistician, said, it's basically a math trick that bears no relationship to the real world. So why are people adopting this at all? Here's some thoughts about potentially why. One is that the authors of the original paper, who are both prominent in sports science, really actively promoted the method. They blogged about it, they held workshops about it, they went around touting it, they wrote lots and lots of papers and opinion pieces about how great this method is. Another is that sports scientists, which to be fair, like many scientists, tend to be relatively unfamiliar with the mathematical details of their statistical methods, sort of rely on others to vet what's an appropriate statistic. It's easy to use, right? With readily available spreadsheets. They said, here's a spreadsheet, here's Excel. You guys all know Excel. Yeah, Excel. Oh man, I don't have to use anything complicated like some fancy software. I can just use my good old reliable Excel. It never has any errors at all, unless you're a geneticist or anybody. So it also, and I think this is actually a plus in terms of its adoption, right? It has a high false positive rate. And if you're in a field like sports science, where most of the effects you're going to be looking for are probably going to be small effects and small sample sizes, it's going to give you significant publishable results more often. And this is good, right? Oh, you did a study and frequentist statistics didn't come up with anything. Guess you can't publish. But wait, what about MBI? Reanalyze your data with MBI. There is an effect. I can publish it. Hooray. Right? So why keep using it? Right? It's been adopted, but it's got all these problems. For the duration of its use in sports science, there was basically never any controversy or confusion among statisticians. They always thought this is not a good method. This is a misleading methodology. But within sports science, if it's used by sports scientists and submitted to sports science journals where it's reviewed by other sports scientists, they might not be able to assess the method. They might say, well, people use this. There seems to be it's our method that we use in this field. This is how things are done. This is an appropriate use of it. They use the right spreadsheet. Hooray! This is from the same article. This is a quote by a biostatistician, Doug Everett, who said, "I almost get the sense that this is a cult. The method has a loyal following in the sports and exercise science community, but that's the only place that's adopted it." All right, so I will note that in the last couple years, its usage has gone down. And that is mostly because of statisticians raising the alarm and encroaching on sports scientists and publishing in sports science journals and telling sports scientists, hey, there's a huge problem with this. You guys seem to be using this, but we know that there's a huge problem. So this is a case study. Many of you may not care about sports science, but I think I'm just using it as an example because I think that this sort of dynamic happens a lot, right? Where there are lots of examples of sort of bad methods persisting and failing to go away, right? Or and also of interdisciplinary influences maybe transforming a field for the better. Right? If somebody else comes in and says, here's a better way to do this, or that's maybe what you're doing isn't so great. The question now I want to ask is, what sort of things drive this effect? Why does this happen? Is it just bad actors not doing their due diligence? Like, is this fixable by just saying individually, you need to do better and being angry at individual people? And I think that, I mean, to some extent, yes, I don't want to just shift any blame from individuals. But also there's something about the structure of the way that science works and science is organized in communities as a sort of sociological force that shapes the kinds of behaviors that emerge. And I want to shift into talking about that, and I'll come back to science, but I want to briefly pause and talk about the media, right? Because I think that this idea is really well articulated this is a very well-known book in media studies by Noam Chomsky and Edward Herman, where they talk about how media, newspapers, television, news programs, etc. And this is written in the 1980s before the internet. But I think a lot of the lessons here are correct, right? In which they say media is completely biased, but it's not because the individual journalists are themselves biased. It's because the whole system is run by powerful people who consciously and unconsciously shape the kinds of people who get promoted to the top and who get access to being media broadcasters and those who don't. There's an interview from 1996 with a BBC reporter, Andrew Marr, which I'm going to show you a very short clip of. In this, it goes on for a while. I've linked there. You can Google this. Marr is very upset at this idea that he might be self-censoring and changing what he's saying because of powerful forces. And so this is his reaction and then Chomsky's response.
How can you know that I'm self-censoring? How can you
I
know
don't say
that
you're
journalists
self-censoring. I'm sure you believe everything you're saying. But what I'm saying is if you believe something different, you wouldn't be sitting where you're sitting.
So this is a well-known take on the media. One of the reasons I bring it up is because last year I was reading a book by the journalist Matt Taibbi, which included a recent interview with Chomsky where they talk about this. And I learned that Chomsky was originally interested in applying these ideas to academia. And he found it too difficult to study academia systematically. And he said, oh, I'll just give up on that because the media there's more data on the media. I can study it better. But he said in this interview, my own view is the media aren't all that different from general intellectual culture, the academic culture. And this was basically the idea, although I hadn't really engaged with Chomsky at the time we wrote it, that drove this paper that I did and published in 2016 with Richard McElreath, right? And we show that, incentives for productivity, to publish a lot, get your papers out, to really build up a CV, drive the cultural evolution of shoddy methods. And this happens without any need for fraud or strategic behavior on the parts of individuals, even though those things do happen, right? So the fact that there's institutional selection for people who produce a certain behavior means that the behaviors that produce those behaviors, let's say if you're selecting for people who publish a lot, then whatever behaviors lead to more publications are going to carry forward, right? Those are the people who are going to get grants, who are going to get hired, who are going to get promoted, who are going to train their students and their postdocs, who are going to publish their methods widely and be copied because of their success and prestige. And their methods are going to spread. And not all of those people, this is consistent with the idea that all of those people are doing what they think is right and what they think is good quality science if they don't know any better. All it requires is for what they're doing to give them a competitive edge, even if they don't understand why. So some follow-up work, both by myself and others, has also looked at what it might take to combat this dynamic. So some ideas we've put forward are things like modified funding lotteries, to sort of use sort of selection on a different things from, let's say, funding agencies. I really like this paper, which is still a preprint, called The Natural Selection of Good Science, which sort of raised the idea that if effort could be invested in theory for better hypothesis testing, then this effect could be sort of reversed if there's strong enough theory, which is a big if. Right? So that's all work that I've done before, and I'm going to sort of leave that there. And I want to talk about the fact that there are other selective forces other than just publishing and impact factor, right? That's the sort of like metrics when we submit tenure packets, or I don't know, it depends on what kind of system you're in. You say, oh, look at these, I've got these publications in these journals and I'm so great. But also there's selective forces from our peers, right? We submit papers to journals and we need to get through peer reviewers, we need to get through journal editors. And there are selective forces like bias, where it's not just about getting a positive result, it's how you're doing it, right? What approaches are you using? People like it often when you're using the method that they use, and they're less inclined maybe if it's a method that you don't use. There's also what we call competence. Now, this doesn't have to imply, this could maybe imply like that the scientists are completely incompetent at doing science, but that's not necessarily what I'm talking about. What I'm talking about is competence to assess the value of a new method in relationship to an old method. And I think this can vary across not just individuals, but also fields and subfields. There can be differences in training in statistical methods or philosophy of science, leaving people less or more able to differentiate methodological quality, like perhaps in the case of MBI and sports science. But also, in some fields, I think the epistemic rewards for adopting new methodologies may not be easy to evaluate. Like if you're building a bridge or if you're an engineer basically and you say, well, here's a better method, you can kind of test it right away. But if you're, let's say, a psychologist who's trying to understand human behavior, the effects are probably small. Knowing that some method is more accurate is difficult to assess immediately. And that just may be the case. And so the question now that I want to ask is how do these forces shape the spread of better or worse methods? Now, this has been modeled previously. This exact question basically was modeled in this really nice paper by George Akerlof and Pascal Michayat. They used a very simple dynamic model where scientists use one of two methods. And then everyone was either tenured or untenured. Those with tenure award tenure to those without. They sometimes make mistakes. So how often do they, sort of correctly assess the better method for the worst method? But they generally prefer better methods. But they're also biased toward their own methods. And so the paper was not extremely thoroughly analyzed, or the model was not extremely thoroughly analyzed in the paper, but the main result is this, right? That in a biased world, when scientists are biased toward their own method, low competence to assess better methods can prevent the spread of those better methods or better paradigms. So this is a sort of a plot in phase space, right? Where here sigma is the share of scientists using the better method. And so sigma is on the x-axis and the first time derivative of sigma is on the y-axis. So you see if there's high competence, right, the better method always spreads because it's better and scientists can assess that it's better. If there's low competence, where they often make mistakes and there's bias, well, if there's not a large enough share initially of scientists using that method, then it's never going to spread. So I like this paper. I think it is a good model, but it's not a very thorough analysis. They also didn't look at, for example, what happens when just a totally new method, and what the conditions for a completely novel method to spread. There's no population structure, and they don't look at sort of how much better a better method might need to be. So we basically did a very similar model that captures basically all their results with a few more in this paper. And our model is very slightly different, but a lot of it is very similar. We were sort of inspired by the Akerlof and Michayat model. So in this model, scientists use one of two methods. We call them A and B for all right and better. The better method has an epistemic advantage, delta. So imagine that all methods sort of on average, let's say produce some amounts of new truths or information, allow us to learn about the world, but some are better than others. Some methods are better and some methods are a lot better than other methods. Some methods are a little bit better than other methods. I think, I hope you can agree that makes sense. So we capture that advantage with this term delta. So if delta is 0, then the two methods are the same. If delta is 1, then the method B is twice as good as method A, etc. Scientists produce research using their method, and it is assigned credit by a reviewer. So this is using this idea that's common in philosophy of science about the sort of the credit economy of science. Right? That what we're actually, sort of what allows scientists to succeed and sort of spread their method and become successful is receiving sort of credit from their peers to say, well, a job well done. Yes, that person is doing good work. Here is some credit. Now, you're more likely to get hired, get promoted, etc. So scientists produce work using their method, and then they submit it to reviewers. Now, reviewers in the model have two properties. They have competence, which is the ability to accurately assess the epistemic value of the work. So if competence omega is 1, then they're perfectly able to differentiate the epistemic value. They'll assign a value of 1 to someone using method A and a value of 1 plus delta to someone using method B. If it's 0, then they have no ability to assess the difference, and they'll just say everyone is the same, and we're just going to assign the mean value of the whole community to them. And then in between is yeah, it's a weighted average. They also have bias, which is the extent to which the assessments are based on the similarity of one's own method instead of on the epistemic value. So if bias is 1, then I don't care what the epistemic value of your method is. I only care if it's the same as method as I use. If bias is 0, then I only care about the epistemic value, and it's a weighted average. So if bias is in between, I care about both. The model then works where an individual's expected credit payoff is a function of 4 things, right? It's their own method, the competence and the bias of the reviewers, and the proportion of individuals in the community who are using their method or the better methods. And we wrote this out as a game theoretic model, and we can calculate this threshold. Don't worry, I'll go through this. This is a threshold delta. So this is how much better does a better method have to be in order to have an advantage and spread against the worst method, right? So this happens, it's more likely to happen when there's greater competence. It's less likely to happen when there's greater bias. And also the proportion of better methods users matters. So the more better method users there are in the population, the more likely you are to get a reviewer who's also using that method, and so bias won't come into play. What we were really interested in, though, is what happens when a novel method that is better, but very few people are currently using it, comes into a community. So it's got this real uphill initial battle. So evolutionary theory, and evolutionary game theory in particular, has this concept called invasion, which is related to an evolutionary stable strategy, which you may know about. And this is the idea of like the fitness of some behavioral strategy or some phenotype is related to the frequency of itself and also the frequency of other strategies in the population. And what we're often interested in is whether a novel variant can spread initially when it's rare. So you do this here by just basically setting P, the proportion of individuals using the better method, to 0. And so imagine, yes, it's an uphill battle. So the question here is, when will it spread? So this is for different values of delta. This is the minimum competence needed in a community for a better method to spread as a function of the bias in that community, right? So what this shows is that the more bias there is, the more competence there needs to be. And for sort of marginally better, marginal improvements, there really needs to be a lot of competence. And for improvements that are not that huge, just sort of marginally better, the model suggests that if there is some substantial bias in the population, it can never spread, even if everyone's fully competent. And even if people have some ability to recognize the value of the other method, if there's enough bias and the improvement is not discernible enough, then that bias is going to outweigh the emphasis on competence, right? This indicates that better methods will often fail to spread. Now, in the Akerlof and Mishayatt paper, this is basically what they concluded as well, and said, well, since science is good and often works, it must be the case that in the past there was good enough competence and low enough bias, so people were willing enough to allow novel methods to come in order for better methods to spread. And I think to some extent that's definitely true. But there's also this issue where maybe not, right? There's it indicates that there's probably a lot of times when better methods couldn't spread or won't spread, right? And it also maybe makes us a little pessimistic for the future if we know that there is bias, right? It indicates that a lot of times methods that are better won't spread even when they're available. and the poorer methods will persist even when there's a better alternative. But again, in this model, there's no population structure. It assumes that communities are insular and only evaluate members of their own communities. I was really inspired by this paper. So I work a lot in the field of cultural evolution. This is kind of so if you are familiar at all with cultural evolution, you may be familiar with the names Boyd and Richardson, who were really seminal people in modeling and thinking about how culture evolves, how what the sort of cultural, social, and psychological mechanisms that sustain human culture and cultural groups are, and formalizing these things in mathematical models. This paper considers the spread of norms, and it, in particularly norms that are group beneficial. So in this idea, you have a norm, and this is basically a coordination problem. If a norm is common, then I should use that norm, and if I use something else, I will get penalized. Always. That's the whole idea of a norm. A group beneficial norm is something that's better for the group. Like if everyone adopted that norm instead of the other norm, it would be better. They'd all do better. But this is tough, right? A group beneficial norm is great when it's common, but it can't invade when it's rare because it's costly, because people imagine contributing a bunch to a public good. Like imagine there's a workers' union and it would be really great if everyone was protected by the workers' union. But if you only have two people being like, come on, and they're putting all their effort into doing this and no one's going along with it, they're suffering costs, and maybe other people are getting the benefit of their work, but they're not receiving any of their own benefit. So it's not going to spread. But here's the thing, they also included a group structure. And they imagine, what if you have groups that have different norms? And sometimes norms from other groups are copied. Because you might say, well, those people in that other group are doing really well. They're doing better than I am, and they have that norm. So maybe I'll try that norm, even though it's going to be penalized in my group. And if that happens enough, then it can sort of increase the threshold of the group beneficial norm enough in the original population that it crosses the threshold to spread, and it spreads. And they showed that this can happen even with very small amounts of intergroup interaction, like 1%. So this got us thinking about the structure of scientific communities, which got me thinking about interdisciplinarity. So it brings us back to the stated topic of the talk. So when I think about interdisciplinarity, I was reminded of this book, Cybernetics. This is sort of published in 1948 by Norbert Wiener, big in the history of artificial intelligence, machine learning, robotics, etc. And he has this nice quote at the beginning where he's very frustrated with the work around the fields he works in. So he said, "Since Leibniz, there has been perhaps no man who has had a full command of all the intellectual activity of his day." And he's going to use man and his because it's 1948 and there's sexism. Since that time, science has been increasingly the task of specialists in fields which show a tendency to grow progressively narrower. A century ago, there may have been no Leibniz, but there was a Gauss, a Faraday, and a Darwin. Today, there are few scholars who can call themselves mathematicians or physicists or biologists without restriction. A man may be a topologist or an acoustician or a coelopterist. He will be filled with the jargon of his field and will know all its literature and all its ramifications, but more frequently than not, he will regard the next subject as something belonging to his colleague 3 doors down the corridor and will consider any interest in it on his own part as an unwarrantable breach of privacy. A proper exploration of the blank spaces on the map of science can only be made by a team of scientists, each a specialist in his own field, but each possessing a thoroughly sound and trained acquaintance with the fields of his neighbors, all in the habit of working together, of knowing one another's intellectual customs, and of recognizing the significance of a colleague's new suggestion. So he's talking about things related to building basically robots. So he's mostly thinking about physics and engineering and maybe some of the basics of like neurobiology. But I think that makes sense because in 1948 the social sciences were pretty immature. But now, right, we have a much more mature social sciences, and I think that this applies equally to these. And I think it's defensible to say that you can't really form a strong theory of human behavior without some understanding of humans as psychological, cultural, biological, and social creatures, right? And you can't understand complex processes without at least some understanding of how complex dynamics work. So this means that all these things are involved from different disciplines in order to construct a good, really good working theories of human behavior. Now, this doesn't mean we all have to become an expert in everything because that's not tenable. What it does mean, though, is that I think learning from other disciplines and proactively allowing ourselves to be evaluated by interested parties with different disciplinary backgrounds is important. I want to talk a little bit about that. So the model that I just presented before involved one community. We instantiated this then as an agent-based model in which scientists were in one of two communities. Again, otherwise the model is basically the same. They use either the all right or the better method. Here they use success-biased copying only within a community. So they're copying methods and inheriting methods from members of their own community, which I think makes sense. If you're in a psychology program, you learn from psychologists. If you're in a biology program, you learn from biologists. But if you're doing work that is related to work in other fields, you sometimes allow yourself to be evaluated by members of other fields. You submit to their journals, you submit to their funding agencies. And this happens with a probability C. So this is kind of interdisciplinarity. So in this model, group one on the left starts with method A. That's the worst method. And group two starts with method B. That's the better method. And here's just sort of a trajectory plot of one run where the better method does in fact spread to group one. Now, we know from the previous model that there is a threshold at which the better method will spread. So here's a plot just using an example. This is a delta equals 2, right? Where, plotting bias against competence. So if you're in a community that is in the gray area, that means if all interaction is within community, the better method will not spread. If you're in the light area, the better method will spread on its own. So what we're interested in is if the worst method is dominant in a population where in the light area, then we don't need interdisciplinarity. If there's low bias and high competence, the better method's going to spread. In the other direction, though, it's not. And so the question then is what happens when individuals interact? So we'll focus on two communities varying by bias and varying by competence. So the pink line is both groups have the same competence, but one is unbiased and one is biased. And so we start with the group who has adopted the worst methods being biased. And the green line is they both have the same bias and they vary in competence. And what we show is that if you have enough outgroup credit assignment, enough interdisciplinarity, then the better methods will spread within a community, even when they themselves are not, don't have the competence and are too biased to let it spread on their own. But if they're willing to sort of be evaluated by an external community, the better method can spread. What happens though if both communities are biased or both communities have low competence? I think occasionally it doesn't, you can get a better method to spread, even if or just to emerge just because that was the path trajectory of that discipline. And they didn't have to be able to evaluate it and show that it was better because maybe that's just the way it came up in that community. So we showed that even if both groups have low competence or both groups are biased, if one group starts with the better method, it will spread to the first group because on average, the better method has an advantage if there's any competence, right? Because people do always prefer the better method. And if they're willing to let other individuals evaluate it in a community where it's common, then the bias won't play a role and it can feed back into the first community. We were a little worried about this though, because this raises the question, can the reverse happen, right? Can worse methods ever encroach on better methods, right? Could a community that starts out doing great just have an influx of individuals not using a great method and the worst method spreads? If there is competence, we find that this doesn't really happen. But we imagine, let's take the worst case scenario. So the worst possible case, right, is that both groups have no competence or completely incompetent. They have no ability to assess the difference between two methods. Where the better method is common, that group is completely unbiased. They don't care. They don't recognize that their own method is better. They just happen to use it. In the first group that's using the worst method, they're really biased. They love their method. They don't know why it's better, but they love it. In this case, right, the better method doesn't spread. Right? Interdisciplinarity, even a bunch of interdisciplinarity maintains the worst method in group 1, and it actually completely eliminates the dominance of the better method in group 2. And basically just you get you get drift, where everyone just sort of goes to, they don't care, they're indifferent between the two methods. And if you have enough interdisciplinarity, it spreads to both communities and everyone's just using whatever method they like because they don't care. And this is unfortunate, but it's also very unrealistic, right? And what we find is if you inject even a tiny bit of competence or even a tiny bit of bias of 1%, you regain the original effect. This is, I think, I like to think of this as a fairly strong argument in favor of the benefits of interdisciplinarity. And I realize I'm running low on time, so I'll try to be quick. What if worse methods carry a productivity benefit, right? So we've assumed here that there's no cost to adopting the better method, that either one, if there's just one is better, one is worse, but I can learn either one the same, and there's no cost. This is potentially a problem, right? So in this, thinking about it in the model, right? If the worst method carries a productivity benefit, then the expected credit per output is still going to be less for using the worst method, but the rate of output could be greater. So like overall, you might be producing more work. And we've shown if there's selection in previous work, right, if there's selection for output in general, this can really be a problem. In this model per se, what really just happens is the threshold just gets pushed back, right? So it still works, but it just makes it harder. It lowers the range of conditions for the worst method, for the better method to spread. But it also would have to mean that the worst method is actually producing a net greater amount of epistemic value. So you get a lot of low information, but not no information studies. That's potentially better if you can do enough of them. Now, I think this is where we run into the limitations of the model framework. And I think if we really wanted to examine this, we need sort of a more sophisticated model that can also include things like selection on output, which we don't have here. But also, I think that there's something well captured by this, and maybe someday I'll combine the two, the bad selection method, the bad science method model in this. I also want to say another limitation, which is that implicit methodologies are not well captured by the model. So there are some methods which aren't part of the report of science, right? There's like, in psychology, you have things like p-hacking and harking, so hypothesizing after the results are known, which are not explicitly described in the methods. They're just sort of traditional norms of how science is done, but nobody puts them in the paper, but everyone kind of knows about them. These are really difficult to catch, because if you read outside your field, you don't necessarily know what's going on. But I will say that there is some hope, because if people become aware of these and then start looking for them and ensure that there are that sort of proving that you didn't use one of these methodologies is important, then an implicit methodology can become explicit. I want to very briefly talk about, well, let's see, how much time do I have left?
2 minutes.
2 minutes. Okay, I'm going to skip the slides where I talk about how economics is all messed up, and just say, so last year I became the chair of the graduate program in cognitive and information sciences at UC Merced, and I gave a talk to the faculty and then to the students about sort of what I thought, our mission should be. And I put this up and to note that, we're not just, if we're interested in behavior or mind or whatever, we're not just a philosopher or a psychologist or a linguist, right? All of these fields contribute to our knowledge and we need to learn from them, but also the arrows go both ways, right? And we should be contributing to all those things. I think this is a point that I've sometimes heard people who start working in an adjacent or a different field, like a physicist who starts working in computational biology might say, well, I'm not really a biologist, so, I'm not worried about it. And I would say, yes, you are. Like, if you're working on a biological question, you're a biologist. If you're working on a social science question, you're a social scientist, right? And so you want to get it right, and you need to learn from everyone that's gonna be able to evaluate you, and you need to be beholden to the standards of whatever that field is, as well as your own. The taken to the extreme though, like, you might think I'm suggesting we should just eliminate disciplines entirely and just all be scientists and learn everything. I'm not suggesting. This is sort of like the earth is flat, right? There's no differences. I'm not suggesting this, right? One, is just totally impractical for various, organizational and funding and training purposes. But I also think that in the model, right, if we were all just one big community, it completely eliminates variation. And so you then revert to the single community model, which is not good. Also, a lot of people have pointed out the benefits of certain kinds of diversity, intellectual diversity, perspective diversity in improving science, right? So a disciplinary structure may be important to maintaining that diversity. I think there's a lot of really cool literature on collective problem solving, indicating that sort of for complex problems, having kind of a sparse network structure where you have different communities that are not immediately influenced by each other working in tandem, and then occasionally being allowed to recombine their information, gives you much better solutions than if everyone is constantly sharing information and everyone knows everything the same, because then you kind of get stuck on local optimum. Okay, so to wrap up, strong bias for current methods or low competence to assess new methods can impede scientific progress. Bias and sort of incompetence are hard to eliminate. Interdisciplinarity can help us overcome this limitation, right? But it doesn't require strong engagement with other fields, and we have to give as well as take. So that's it. Thanks.
Excellent. Awesome. Thank you, Paul, for this amazing talk. I could also say briefly that everybody should check out this Chomsky interview because it is amazing. Andrew Marr, BBC Chomsky, just Google it afterwards. But now I'll open it up for discussion. So you can raise your hand by virtue of the chat, I think. And there's a more natural ordering. Yes, Denny, go ahead.
Thank you, Paul. Wonderful talk. Enjoyed it a lot. I had the question that in your model, you make a distinction. Basically, you have this dimension of the model, the methods, which are sort of unidimensionally ordered on good to bad. And there are scientists who are sort of unidimensionally ordered to competent or incompetent. And so, well, there's something to that. I have found, as I personally developed, that the idea that there are good and bad methods, the good and bad methods aren't actually orthogonal to competence. So a good statistician, for instance, can use crappy methods and still, leverage them to good results. Whereas even the most fantastic methods cannot save somebody who doesn't really get the underlying concept. So you often, I think that's often when people champion, for instance, Bayesian methods, which are beautiful, but a Bayesian method or null hypothesis testing you know, for if the user is not really competent, then will it really advance us? So I was wondering whether you think that these things are really orthogonal, actually, whether you can vary them independently.
Yeah, I thank you for that. That's a great point. I actually agree with everything you just said. I think that there is a way to interpret the model as, it doesn't have to be, let's say, a statistical analysis technique like Bayesian versus frequentist or something like that, but it could be an approach, like taking a lot of care and doing a lot of sensitivity analyses or whatever. I think that to some extent there can be methods that are adopted or not adopted that are more practice-based than sort of technique-based. I think that there's still sort of the reason why even today we use this sort of apprenticeship model for training scientists is because there's a lot of tacit knowledge that you need to do all this stuff. They're very hard to sort of say, this is the way to do it. Otherwise, you could just say, here is the protocol for science. It feels like what some people want, and it's also a problem. So, I do think that though that there is a limitation in thinking about how a better method spreads. Like the model is very simple. It's just sort of like, I have a method and then I can, someone else is using a method that seems better. I'll just adopt that. But like in reality, there's a lot that goes into it, right? Well, I mean, another way to interpret the model is that doesn't happen at all. And it's really new scientists come up and they think, who am I going to learn from? Who am I going to get trained from? And that technique, and I think actually that is a better fit for the model, because I think you're more likely to interpret the approach from, let's say, an advisor than you are from just somebody who seems to be doing well, who you want to adopt. And you're more likely to say, oh, Bayesian versus frequentist or something. But models are, models are stupid, right? But like I still think that there's something to this, but nothing's perfect. It's a longer conversation, but yeah, your point is well taken.
All right, Bruce, and then Renske, and then I, because I don't know how to raise my hand, actually. Bruce, go ahead.
Thank you. Paul, really nice model, and touching on issues I'm very interested in terms of interdisciplinarity and how bad science gets around and stuff like that. So really like that, and it will cause me to go and read 3 or 4 more of your papers. I've already collected 2 more from the last one on social identity, and now I've got 3 more on science, so that's good. I just wanted to clear up what you thought about the status of your model, because this is not an empirical. You don't relate your model empirically. It's very plausible, and in fact, I would believe it. I don't believe it, but it's not something that's we've validated or checked. Is that right?
Yeah, that's
the sort of way of thinking about science.
It's the way of thinking about science, and
yeah.
we have some case studies, and in the Akroloff and Mishaya paper, they have some case studies, based on their model. But no, it's not. I would say it's not even at this point. I wouldn't know how to go about really validating the model.
Yeah, very hard.
Currently in
hard. Yeah, I don't know. Yeah, I mean, what would have to get a whole lot of data from somewhere, and I don't know where one would get it. Maybe, I mean, from something like World of Science, if they have lots of citation data and you trawl through it, but it would still be hard. No, I quite agree. It's really difficult. Doesn't that mean you shouldn't be a slightly little bit more cautious about suggesting cures, since this is a purely theoretical model?
That's a fair point. I think I base my suggestions based not just on this model, but on lots of observations that I've made. But I will say that, you're right. I don't have. I think it's very. It would be accurate to say that I don't have sort of a airtight case for the things that I'm suggesting. I'm saying that based on this model and other models and my own observations and other things I've read, I think that it makes sense to do this.
Yeah. No, I full sympathy. I've made models that are far more abstract than yours, with even less hope of being empirically validated. So anyway, yes, thank you very much.
Thanks. I will just also add, Bruce, I've read many of your papers as well, and enjoyed them.
Yeah, we're among friends. All right, Renske, go ahead.
Thanks for the talk, Paul. I wanted to ask you about one of the last points you made, which is actually quite close to my heart, when you mentioned that when you do interdisciplinary work, you really are in that field. And so what I encountered myself is that there's a difficulty when doing interdisciplinary work, which is related to the language that you speak. So you can come along from a different field saying, I have a better method. But then often what I see the response being, and that is not completely unjustified, is, but you're answering the wrong question with your better method. So at that point, who is left to say what's better? And this is I think a real problem. Like at some point, who evaluates this? And can you comment on that?
Yeah, I think you get at a very deep question or thing about science in general. And this is something I've thought and written about, although not as much in this context. So thank you for that. I think science and sort of hypothesis testing and generating hypotheses to test, and the process of doing science is decomposing the world into a particular system we're interested in, and then saying, I'm going to decompose that system into parts. These are the parts of the system. Let's say it's people, and they have these properties, like various psychological features or behavioral choices they make. And these are the interactions and relationships that I care about. So those are the parts that are salient to the way I'm thinking about the world, and therefore structuring, using as a scaffold to build hypotheses. And depending on the questions we want to ask, a different decomposition is useful. And so there isn't sort of a true decomposition because the world has everything, right? We say, well, these are the parts that matter to asking these kinds of questions. And there may be a different set of parts that matter to asking different sets of questions. Now, it's not completely interchangeable, right? There could be, some decomposition is better for asking a particular question, or if I change it, it becomes better for asking a particular kind of question than another. But, the questions we ask drive how we think about the world. And so if we're asking, there are sort of two perspectives on what you just said. One is that maybe it's true that like the way you're thinking about things is right for answering those questions, but it's not for answering the questions I'm interested in. But another perspective is you're asking the wrong questions, or the questions that you're interested in are actually not going to be answerable in a good way. And there's another framing and a different decomposition that will allow us to ask maybe slightly different questions, but actually be more informative toward answering those questions. Now, this is all very vague, what I've just said, because I don't know the specific, it would be different for every system. So I think that there is some validity to that, but I think it has to be done on a case-by-case basis. I could talk for like an hour on that, but
me too. I totally agree with this. And I think ultimately it becomes really a matter of because I like the idea of perspective switching, like answering new questions and bringing a new perspective to a field. But it ultimately will boil down, I think, to being able to speak each other's language and then trying to come to a common ground. But that's a whole nother story, I think.
Yeah, I agree. I also will just say, I think that, it means that on the one hand, it's why working together is tough but necessary. There's this great blog post by John Wilkins who talks about, interactions between modelers and biologists, and he was basically like, yes, you can't learn everything, so it's good to work together, but the modeler has to talk. They have to talk to each other, and the modeler has to learn from the biologist enough about the system to make the model work and be realistic. And the biologist has to work with the modeler to understand exactly what all the parts of the model are actually doing and all the assumptions, what they really are, to make sure that they're plausible. And they both have to do work to make that happen. You can't just, the biologist can't just give their theory to the modeler and says, go prove this with math. Right? There has to be an interaction. Yeah.
Absolutely.
Okay.
Thank you.
Yes, I have a quick question. So to me, it seems, so I'm mostly interested in the non-equilibrium phase, right? So in the MBI example, they have that, and then the statistician do some things, and then I'm interested, like, what's the dynamic, and then maybe at some point it settles in some equilibrium, as you do in your model. I think you're only looking at the, as far as I understand, please correct me if I'm wrong, the equilibrium case, right? If I iterate forward.
Yeah, the
do you
model
have
is really, it's a
yeah.
model of basically equilibrium selection. Yeah. No, I think you're right. Like a lot of the interesting stuff for a behavioral science scientist is how the process works from going to one state to another. And in real life is almost never equilibrium, right? So it's
exactly.
constantly dynamic.
But are there any interesting equilibrium things? I mean, did you look at your simplified model? Is there anything cool happening until it reaches equilibrium, or is it really, is that even not even a question
model,
you would?
It kind of, there's sometimes stochasticity, and it takes a little while where, like, if you look carefully at the dynamics, sometimes like the level of adoption will kind of go up and then go down and then go up, and then like it crosses a threshold where it's selected internally and not just externally, and then it rockets up.
Yeah.
Right. And there's still a little jiggling, but it's sort of like, and then so what really, the argument here is, in a sense, that interdisciplinarity allows enough noise, biased noise, to be injected into the system where you're just kind of like, it increases adoption enough that occasionally it will be popular enough that it'll catch on and take off.
Yeah.
And that's really kind of what the dynamic in the model is.
Right.
It's worth considering whether that's really what happens. And I don't know the answer.
Yeah. I mean, in my perspective, you often have, like, there's some cool thing, like, say, dynamical systems theory, early warning signals, critical slowing down in some other field, and then it gets, put over in psychology and so on. So everybody's like hyped, and then there's this adoption phase, and then later you have this crashing down, and we're like, oh, actually, this doesn't really work that well, and so on and so on. And then maybe it reaches some equilibrium, but yeah, who knows?
Yeah.
But
yeah. And I mean, it's also like there are new synergies that come up. It's not just like a method goes from one field to another in real life, right? And it's like, oh, we'll just use that, and now it's our method. It's usually like, oh, we can use that and change it to, and this gets to Renska's question also, like, and change it sufficiently that it works for our questions, and we give new perspectives on it. I think about, like, the adoption of network theory in the social sciences. Like, graph theory had been happening for a long time in mathematics and computer science, and then all of a sudden you get a couple people, and actually, it came from mathematics and physics, but people who are like, oh, look at that, like, we can think about the structure of social networks and use all these concepts we've been talking about in graph theory for decades, and then it just becomes, it explodes, right? And lots of people adopt network theory, but also social scientists, behavioral scientists, cognitive scientists come in and say, well, but there's all these things about networks in our systems that you guys haven't looked at, so now we have to adapt the methods in these new ways, which and that's not in the model at all. But I think the interplay between sort of selection and adoption on the one hand, and innovation and change on the other, is something that I think is hugely important. And I actually have a couple of grad students now who are kind of working on trying to build models of these interplays. But really, like, it's very hard to think about both of them at the same time. But I think that it always is both of them.
Yeah. Nice. Okay, I think we have a couple of questions from the chat. Peter, if you're here, you can ask it. Otherwise, I read it.
Yeah, I'm happy to ask it. It's actually just a follow-up to a question that was asked before about providing empirical evidence for the modeling. So it's I was just wondering if there are more informal ways of providing evidence, or if the case of MVI that you mentioned, if your model makes any specific predictions for historical cases, or if it would be interesting to ask people in the field of MBI, for example, like when you were introduced to these critiques, how did you respond? Like, were you excited about adopting these new methods? Did you understand the statistician's critiques and stuff? Because I guess implicitly you assume that, right, when you say that there's interdisciplinary influences on a subfield.
Yeah, so there's a specific question and a general question. I'll answer the specific question first, which is that, so we didn't talk to anyone specifically in sports science about MBI, but we did talk to the journalists who had talked to them. And so it was actually Kaylin who had like a long phone conversation with Christy Ashwandon, who'd done all the journalism on that. And so, and we talked to Kristen Sainani, who was the statistician. So we had phone conversations with both of them in the process of writing this paper, and got things from their perspective. I think that it is a fair point to say maybe you should talk to one of the sports scientists too, and we didn't do that. And my impression is it happened basically the way we wrote it, but obviously it's there's a lot more detail. And I actually think if you read Christy Ashwandon's articles, which are all cited in the paper, it gives a lot more nuance about what was happening with MBI. The general case would be fascinating. It's really difficult to do. I mean, history and philosophy of science is a major, Kaylin is more situated in that field, so she's sort of better equipped to do that than I am. But I mean, it's very difficult. If you ever, one of my favorite books on like the history of science is David Hull's Science as a Process, where he sort of talks about like the evolution of methods and approaches in evolutionary biology over decades. And it's very slow going, and you have to have a lot of detail. And he was able to do that because he was kind of present for a lot of it and was able to talk to people. If you look further back in history, like we have selection bias, where we don't know all the things that failed. I think that there is potentially a lot more detail that could be filled in with what is available, but there are also limitations to that. That's as far as I can. Sorry, I don't have a better answer.
All right, then we have one question from the chat. What do you, maybe you can rant about economics a little bit. What do you think about the fact that PhD programs incentivize individual work rather than interdisciplinary group work? It's a sociological question.
Yeah, this is we didn't really write about this that much, although we reference it and kind of obliquely in this paper. But I've written elsewhere a reasonable amount about incentives and how they shape science, and other people have as well. It's an issue, right? I mean, it's not just an issue with training though, right? It's the way PhD programs work. It's also the issue with who gets rewarded and who gets hired, right? Like personally, like I would love to have like a dedicated programmer in my group whose job it was to build and analyze models. Other people in my group come up with the models, talk with them, work with them to build it, and then they do all the sort of deep coding work. And as well as data analysis too. I'd love to have someone who's like, oh, I'm like, okay, so go scrape this data from the web, or here's a data set, like I need you to analyze it. I'll tell you how to do it. You just have to do it. I would love that, right? And there are people out there who would love that kind of job, who are much more detail oriented than I am. And currently, there's very few funding models that allow those people to sort of have permanent jobs in academic science. And I think that's the larger problem, because we have this sort of obsession with everyone must be a principal investigator doing their own individually driven work. And if we're going to have real team science, we need to, not just think about the diversity of perspectives, but also the diversity of jobs and roles, and have, and not make it so that the PI is this sort of, that is the top position and there's no one, everyone else is an underling, but rather like it can be a collaboration with people with different skills. And that's really hard to get from where we are now to that. And I don't know exactly how, other than to just yell and scream a bunch and get more people to yell and scream. And maybe if enough people yell and scream, things will change.
Yeah, nice. Maybe there's a tipping point when we all scream. Are there any other questions for Paul? Otherwise, I would thank you all for coming. Paul, for being with us for this talk, for the discussion. It was very nice.
For having me. It was fun.
Yeah, awesome. Briefly, next week we'll have a talk on modeling tipping points in climate and in social systems, if you're interested. And yeah, we upload the recording and send it to your friends. See you. Have a good weekend, everybody. Thanks for coming.